All right, today we are diving deep into the absolutely revolutionary engineering behind SpaceX Starlink. We're talking about one of the most ambitious infrastructure projects in, well, human history, and we're going to break down exactly how it all works. But first, let's start with a kind of wild question. What if the fastest way to get your data from, say, New York to Tokyo wasn't through cables buried under the ocean, but through the empty vacuum of space? Just hold on to that thought because it is absolutely central to the genius of Starlink. So here's our game plan. We're going to go on a sort of cosmic zoom, starting with the basic physics, then diving into the hardware, the mind-bending space laser network, the sheer scale of manufacturing, and finally, what all this means for us down here. First things first, why does Starlink even need to exist? Well, it all boils down to a fundamental problem of distance and, the speed of light. It's really a tale of two different orbits. Okay, so traditional internet satellites, they hang out in what's called geostationary orbit, or GEO, and that is a staggering 35,000 kilometers away. Starlink, on the other hand, puts its satellites in low Earth orbit, LEO, which is more than 65 times closer. This one decision, this proximity, is the key to basically every single advantage Starlink has. Because that huge distance for the old satellites creates a massive delay. We call it latency. We're talking over 600 milliseconds for your signal just to go up and come back down. For anything in real time, think a video call or trying to play a game online, that kind of lag makes it pretty much unusable. Now look at this. Because Starlink is so much closer, its latency can drop to as low as 25 milliseconds. That is an absolute game changer. For the first time ever, it makes satellite internet a real competitor to ground-based stuff like fiber and cable. Okay, so the physics totally checks out, but what's the actual hardware that makes it all possible? Well, it really comes down to three crucial components in this big cosmic data relay. It's really a three-step dance. Your terminal on the ground, the dish, sends a signal up to a satellite. That satellite then shoots the signal back down to a ground station, which is physically plugged into the rest of the internet. And this whole trip happens in the blink of an eye. So the first piece of the puzzle is that user terminal, famously nicknamed Dishy McFlatface, or as Elon Musk put it, a UFO on a stick. But don't let the cute name fool you. This thing is an incredibly sophisticated piece of tech. The real magic inside Dishy is something called a phased array antenna. Get this, without any moving parts, it can electronically steer a beam of data, perfectly tracking a satellite that's zipping across the sky at 27,000 kilometers an hour. It is pure applied physics in action. All right, let's move on to piece number 2, the satellite itself. Each one of these is just a marvel of mass-produced, miniaturized engineering. They've got their own antennas to talk back to us, tiny ion thrusters to dodge things and stay in orbit, and, this is the important part for later, laser links to talk to each other. And that brings us to what is, without a doubt, the most futuristic part of this entire system. You see, Starlink isn't just a bunch of individual satellites. It's a mesh network, in space, connected by lasers. Here's why that's so huge. The early satellites had to be in direct line of sight of a ground station to work. But with these inter-satellite links, the space lasers, the satellites can just pass your data between themselves. That means if you're on a boat in the middle of the Pacific, your signal can just hop from satellite to satellite to satellite until it finds one that's over land. It's what makes truly global coverage possible. And this, right here, is why that question I asked at the very beginning was so important. It's a fact of physics. Light travels about 50% faster through the vacuum of space than it does through glass fiber optic cables. So for really long distances, Starlink's laser network can actually be faster than the undersea cables that power our internet right now. It's just wild. Okay, so the tech is brilliant, but having a few satellites is one thing. To cover the entire globe, you need thousands, and that requires a level of manufacturing and launch capability that the space industry has, well, never seen before. Just look at this number for a second. Over 10,000 active satellites. To give you some perspective, that's more than 65% of all active satellites currently orbiting the Earth. It's not just a constellation, it truly is a mega constellation. And they are moving incredibly fast. I mean, from the first prototypes in 2019 to what they have planned for the near future, each new generation is a massive leap forward. The upcoming V3 satellites, they're designed to have more than 10 times the capacity of the current ones. you can really see that evolution here. The satellites are just getting bigger, heavier, and exponentially more powerful. They're going from just providing broadband to becoming a platform that can connect directly to a normal cell phone in your pocket. So you might be wondering, how is a jump like that even possible? Well, the answer is one word: Starship. The Falcon 9 rocket is an incredible workhorse that built the network we have today. But Starship is designed to carry over 4 times the payload. It's the key that unlocks this whole next generation of Starlink. So let's zoom out one last time to the widest possible view. I mean, building a literal internet in the sky is a monumental achievement, right? But it also comes with some really profound and complex consequences for all of us down here on Earth. Right from the very beginning, the scientific community, especially astronomers, raised some serious red flags. The problem is, this sheer number of satellites reflecting sunlight creates bright streaks in telescope images, and that can completely ruin crucial scientific data about our universe. Now, SpaceX has taken steps to try and mitigate this, but it's a debate that is very much ongoing. And this really gets to the heart of it all. On one hand, you have this incredible promise, connecting people who've never had good internet, providing a lifeline in disasters, maybe even bypassing censorship. But on the other hand, you've got real risks: more space debris, a powerful new tool for geopolitical influence, and, of course, questions about who controls this global flow of information. It's the classic double-edged sword. Which really leaves us with one final and absolutely crucial question. This technology is moving so much faster than any government or regulation can keep up with. So, as a private company builds a global utility in orbit, we have to ask ourselves, who gets to write the rules for this brand new frontier?